Dr. Pat here, looking at linear functions. So that's what we'll be playing with today. Now, one of the things I'm going to start off with tables of data just to kind of getting the idea about linear. What does it mean? It's meaning about the same amount of change. That's what makes a linear. It's straight line. What makes the graph a straight line? It's because of the change. Okay, so that's what we're going to be looking at, how things change. So I'm looking at this first data point table up here on the left, and I'm looking at the change in the y values, the function itself, and I'm seeing that this is going down 25. But when I talk about change, I got to keep track of how the x's are changing as well, because not every table of data has the same increment of change for the x's all the time. So you got to be careful about your data points. Okay, so my first one looking at here is this is negative 25 per change of 2x's, and this consistent that way. That's also another negative 25 for differences of 2x's, and this last difference right here is also another negative 25 per 2x's. That means these are all similar. That makes this a function, a linear function I should say. And that's what we're looking at. We're looking at how things are changing. If the change is consistent, then we have a linear situation. Now remember, in real life, you don't get exactly the same amount of change each time because real life is messy. And so as long as we get very close or similar amount of change, then we're okay with saying a linear model could work. Looking at this next set of data, the f function, once again, I'm looking at how the y value changes and is that consistent. And so for this set, I've got a change of 20 for each of those y values, and each of the x values I have a change of 2. That's consistent, similar results, so that's a function. Okay, my next one that I'm looking at here is the one on the bottom left, and this is where I get some inconsistencies in two ways. One of the things I want to bring your attention to is look at the x's. I got a change of 2, change of 4, change of 2 again. So this middle change right here, I have to really indicate that it's per 4, so that's important to keep consistent that way to analyze your numbers. So when I'm looking at the first change, I've got a change of 25, increase 25 for an increase of 2 x's. And then for this next one, I had an increase of 75 for 4 x's. Okay, so that's different than the previous one. If this would have been a 50, then I would have been happy, because if I double the amount of x's, then I should double the amount of change in y's. That's not so. This is a problem, especially when we go to the third change that we looked at. That's a change of 125 in the y values, change of 2 on the x's. That is really different than the beginning one. And so these are different. They're not similar. So this is not a linear situation. For the last one that we're playing with here, just want to bring your attention to that 4 and 8 is where we have a big change right there, similar to what we had on the previous one. But in this case, notice that we doubled the amount of x's and we doubled the amount the change in the y's. So that's okay. That's consistent. All right. So when looking at this, when we're looking at the changes in the y's, one of the key things to keep in track of is how the x's change. As long as it's getting consistent in terms of you double the x's and you double the y's, then you're okay. This is similar as well. Okay. So that's what we got playing with. So when we're looking at that change on the previous, the tables, it was all about I was doing 25 per 2, or I kept in track of how the y's were changing and how the x's were changing, and that is your slope formula. Your change of y's over your change of x's, because it's the relationship of how the y's changes, but we got to keep track of how the x changes as well. And so we're using math people like to use the delta here. This is a triangle, it's the delta, and that's our math sign for change. Okay, so that's what we're playing with. And so just for an example here, let's just find the slope of a line through these 2 points, 3, 4, and negative 1, 6. So what we need to do then is put it into that fraction. So it looks like what I did here is I called this point here my second point. Here was my first point. And so what happened was I put my 6 on top, put my negative 1 on bottom. The key thing here is the y and x value of the data point have to be on top of each other because of that minus sign. That minus sign, it's important that we keep vertical our data points. And so that's why you see the 4 over the 3 there. Make sure you put the y's on top, the x's on the bottom, and then you start reducing out and you get your answer of -1/2. And so some people would say, or would have questions like, dude, you put this as the second point and this one as the first point. Could I switch those around? And yes, you can. You can switch the order of your data point. The only thing you got to keep track of, keep consistent, is your data points x and y values are above each other. So we can move the 4 and the 3 out in front. What would happen is it would create a -2 on top, because then we do 4 minus 6, and then we'd have 3 minus a -1, which makes a +4. When you switch the order, who is 0.1, who is 0.2, all you're doing is just moving the negative up to the other spot. It's either the x's were change was negative or the y was changed was negative. And so that's all it's going to do. We'll end up with a -1/2 either way. Okay, let's end this video with just an example of making your equations. So we have 2 data points. We want to find the equation through those 2 data points. All right, one of the first things that we're going to need to do is find that slope. And so change of y's over change of x's, making sure your data points are on top of each other in terms of the x and y's. We get a slope of 2/3 in this case. This +2 that you see down here was because I was doing minus a -2, which then creates that a +2. And then I'm going to use the point slope form. This is another way of doing it. I like using it whenever I do it, use it because it matches a lot of examples that I have for my applications. And so I've got my slope of 2/3. That's going to be putting right in there. And then you can take any point that you want. Either one of these points will work. I'm just using the first one there because, you know, it's just right there. So I'm going to plug that x value in there. I'm going to plug the y value in. And that's where we're seeing here. I got my 2/3 slope, my x value plugged in there, my y value. And so now the next thing to do is just kind of simplify this. So let's expand that 2/3 through and then bring the 5 over to the other side. So 2/3 times x right there. 2/3 times 2, that's a +4/3 plus 5. 5 is the same thing as 15/3, and that's where you're seeing this 19/3, 4/3 plus that 15/3. And that will do it for my linear beginning of the linear functions. And this will be part 1, and then I'll move on to some examples, some word problems. Thanks, and have a good day.